sound. I think it's time to start this showcase. My name is Per Einar Pedersli, and I will be the moderator of today. I work in Norwegian Public Road Administration, and I am a project coordinator of NordicWay2. I'm very glad that so many of you have taken time to join this meeting. This showcase was originally scheduled in May, but due to the pandemic, we, as many others, had to find a new day on how to do it. So now we are here in the digital world, but hopefully it will be a good showcase. I will ask my colleague Erik Olsen, who is representing the management in NPRA, to join us, and he will give us all a welcome. And after that, I will come back with some more information. So, Erik, let's start the show.
Thank you, Per Einar. First of all, a very warm welcome to you all to this showcase of the Norwegian pilots in the NordicWay family of pilots. I say the family of pilots because NordicWay has really brought us together in the Nordic region. Denmark, Finland, Sweden, and Norway. It has provided us with a platform for cooperation between the road authorities, industry, and research institutes in the field of cooperative, connected, and automated mobility. Together, we also have a voice in the international fora, in standardization, and towards the European Commission. And we have been able to bring forward Nordic perspectives to the international community. So cooperation across borders is fundamentally, I would say, in this field. Finally, I would like to thank all our partners who have worked together with us. It is really a long list of organizations from the private and public sector in all our countries. You made this possible. And finally, also a warm thank to the European Union that co-financed the project. We have had a very good cooperation and support from the Commission and the project officers that have followed the NordicWay project. And with that, I would say, enjoy the day. Thank you.
Today's agenda, we have two sessions. We have 2 hours before lunch, which we now have done the welcome, and I will now presentation of the agenda. Then we will have introduction to the Norwegian services. We will hear about the test sites in Norway. We will have presentation of the interchange, the heart of the service ecosystem. And then we start to present the services and what technology has been used to make them operable. Then we take lunch, and after the lunch we continue with the technology and services. And we will hear about Nordic Tour. And we will have also an interesting presentation on the short-range communication services and future perspective. And after that we will end the showcase presentation. And we start with an introduction to the Norwegian services, and the speaker is Thomas Levin. So welcome, Thomas.
Thank you, Per. So my name is Thomas Levin. I work in the Norwegian Public Roads Administration, where I mainly work with readiness for automation, trying to figure out what we as a national road authority need to do to get the benefits of automation that's coming. Today we're going to talk about the services that we have piloted in the NordicWay2 project. Basically, they are the weather and road conditions, slow and stationary vehicle, signal violation, traffic ahead, mobile roadworks warning, road and lane closure, cooperative collision warning, and in-vehicle speed limits. These are all use cases that are good and work well in mainland Europe. But Norway, as you can see from both the picture and the map, is not so mainland Europe. So basically, if you look at the challenges we face in Norway, you can see that most of our goods producing industries are located along the coastline and in remote areas. A whole lot of fisheries, fish farming, fish slaughterhouses, a few shipbuilding yards, furniture production, and all sorts of goods producing industries are out in the districts. The trouble with these factories are typically that they are the cornerstones of the society. So if you remove or move the factory, you basically move a whole village. So politically in Norway, we want these villages to stay where they are, and that gives us a communication challenge, how to get goods to and from the market. The trunk road network in Norway is rather long. From Oslo to Kirkenes, it's 2,500 kilometers, and it will take you 34 hours of effective driving. So we have a long country, but we also have a lot of weather in this area. We have fjords and mountain passes, and you can go from a fjord to the mountain in less than 45 minutes. This also gives us challenging with weather because you move through different climatic zones. And also our typical winter is what you would call extreme winter days in Europe. So the focus on the Norwegian services is basically freight transport. How to get the goods to the market. That's how countries make their money and how we survive. We have a lot of oil, but times are changing and we need to get our other goods to the market. And basically the markets are mainland Europe, Russia, and Asia. And there is a problem because nobody is in a bigger hurry than a dead salmon. Norway actually export fish from the fish pen and put it on the table in Japan in less than 36 hours. This means that every part of the road is very important if you are to make the deadlines for the different transports. So the research question for us was, how can we make CITS services useful so that we don't have to build roads, but can support the roads and tunnels that we have at the moment? Yet again, the challenge is to be solved. We've tested some smart routing, and the smart routing is so smart that it routes us through it from will actually hour. The right-hand side shows some of the climatic issues. It's published by the Met Office. So the temperature down in the Skibotn Valley was 14 degrees plus, while at Kilpisjärvi in Finland, it was minus 11 degrees. And this trip takes less than 65 minutes. And even some of the good winter days can be bad because it depends on the equipment you are using. In Europe, using 2-axle trucks, that works mainly most of the year. In Norway, under winter condition, 2-axle trucks is a poor combination. You're not able to get the amount of load on the driving wheels. So on the top left picture, the guy stops in the hill. This is in the Skibotn test area. On the right hand picture, 40 minutes after, he figures out it's time to put on chains. The picture below is a trailer that's scissoring. So basically it stopped going up the hill, could not get enough traction, and starts going down the hill again, and that's how it ends up in this peculiar situation. And also when you're going uphill, big trucks come behind you and they cannot overtake, and hence they have to stop behind the other truck, and then you sort of get a queue even if there are very few vehicles. And these queues can take quite a long time to disperse when they put on the correct chains. And of course, we have some more issues. We have some snowstorms. This is down at Skibotn. It's snowing. The trucks have piled up at the local gas station. The top right-hand picture is for our Danish friends. A Danish driver is figuring out how to put on snow chains. And the picture, you could think it was concrete with some water on top, but it's solid ice with water on top. And then again, we usually use salt and sand and stuff like this to remove some of the ice. Well, that also attracts the reindeer to the road when we start using salt. And in other areas, we have narrow passages, for example, tunnels that are so narrow that you can only fit one truck in them at a time. So basically, they have to drive on the central line. So our question and our piloting schemes were developed so that we would be able to test how these services would give value under Norwegian condition. So they are a bit different than how you expect them to be implemented in mainland Europe. But if we are to finance and use a lot of state money on the development of CITES in Norway, we have to make sure that we can get value out of the services that we test. So from now on, you'll hear a bit more about the services in the specifics of them, but also a bit about the test sites. So then I'll give the word back to Per Einar.
Okay, thank you, Thomas, for this introduction. And as Thomas said, we will now hear about the test sites in Norway. The first speaker of that is Jorunn Rydevold Levi, that will focus on the road E8. And then Ragnhild Beckman will present the road E6. So, Jorunn, you can now join the meeting and make your presentation.
Thank you. My name is Jorunn Levi. I work for the NPRA, and I will present the infrastructure and reference systems at the test site on E8. This test site is a 40-kilometer road section, and as Thomas said, the weather and driving conditions change significantly from the fjord at Skibotn to the mountain areas by the Finnish border. As this is an important transport route, the heavy trucks face challenging conditions, especially in winter. And the map on the left side shows the main problem areas where Halsebakken and Garderborgbakken are challenging hills. Close to the border, the problems are mainly due to drifting snow. A number of technical installations have been made along the road section to facilitate the testing of new technology and solutions to improve the situation for the transports. 10 main sites are equipped with power and fiber network for communication, as well as cabinets, technical buildings or masts for mounting of sensors and other equipment. These locations are chosen in order to cover the main problem areas where heavy vehicles most often need assistance, and also sites suitable for detecting, warning, or stopping oncoming vehicles. Most of the activity and installation of equipment have been in Garderborgbakken concerning slow and stationary vehicles. Power and fiber communication in the districts can give some practical challenges and will drive cost of installations. All cabinets, masts, and technical buildings along the route are connected to power and fiber. This was achieved by digging 4,700 meters of ditches for underground power cable and installation of 250 meters of overhead power cables. Fiber network cable is installed along the entire valley from Skibotn to the border. All main sites are connected. A new 600-meter long road section was built at Silobakken to create suitable conditions for traffic monitoring with various technologies. We have installed in-ground sensors such as way in motion, inductive loops, and acoustic fiber. Technical buildings have been installed at 2 sites, Silobakken and Garderborgbakken. Other locations are equipped with cabinets and masts, and these are some examples of this. To facilitate the testing of new technology, we have installed reference systems with sensors for weather and traffic registration. We have 4 weather stations with specifications according to the national standard in Norway. Cameras are mounted in both directions on 10 locations to give an overview of weather and road conditions. 4 cameras have close to real-time camera feed. The test site has 4 installations of inductive loops for traffic registration. Travel time antennas reading autopass tags are mounted in each end of the demonstration site. 2 types of sensors for way in motion are installed in both directions at Sitnodieva and Silobakken. Kistler linear quartz sensors and piezoelectric cables. These have the same layout and data loggers as the automatic speed enforcement system in Norway. This was a short presentation of the reference systems on the test sites. Other sensors installed will be presented later today. Then we move on to Fatterø.
Hello, my name is Ragnhild Beckman. I also work for the NPRA, and I will present the test site at E6 Fatterø. Fatterø is an intersection on E6 between Oslo and the Swedish border at Svinesund, with high speed and heavy traffic. A common situation is spillback queue on E6 from the ramp in the northbound direction. The test site at Fatterø has about 40,000 vehicles on the E6 driving through every day. The speed limit at the site is 110 kilometers per hour in the summer and 100 in the winter season. Instrumentation on the test site. The test site is equipped with a technical building, as you can see to the right. We also have 4 RSU mounted on masts, as shown in one of the pictures. There will be shown a map with the locations of the RSUs on the next slide. A system for queue detection based on inductive loops has been installed at the ramp from south, as well as variable message signs, both south of the intersection and north. These are well-known technologies, and it will be used as a reference for new technical solution being tested on this site, which is G5 technology. Power and fiber communication has been made available in the intersection as well. This picture shows all the 4 RSUs in the test sites and their location. The picture is also showing Avantis web application, which has been developed for the pilot. The reason why we also mounted the RSU further south was because of the range of the radio signal. We wouldn't see the whole queue at once if we only had the 3 in the intersection. This slide shows a more detailed map from the test site. Here you can see the ramp, which we are struggling with spillback queue on, and the roundabout in the other end. Also some pictures from the inductive loops and the building of the cabinets. And what makes this intersection special? We have a difficult topography with a hill in the middle of the intersection, which you can see in the pictures. There's a bridge, a tunnel, and a big difference in heights. Another thing which makes the test site challenging is that there are several sources which can develop noise disturbance to the radio signal. like the shopping center behind the hill, the high voltage cable which passes the test site, and other roadside equipment like travel time sensors. And that was a quick introduction to the test site at E6.
Now we hand over the floor to Christian Berg-Skjetne, who will present the NordicWay Interchange, which we have named the heart of the service ecosystem. So welcome, Christian. You can start now.
Thank you, Einar. Let's see. So thank you. My name is Christian Skjetne. I've been leading the development work on the NordicWay Interchange in the NordicWay2 project, both in Norway and in the let's see, the Nordic collaboration, the development as well. So the goals of the interchange system that we have developed in NordicWay is to facilitate a real-time data exchange between different actors. It started out as just a method for exchanging information between the actors in the NordicWay1 project, but it quickly grew into a system that we wanted to be able to scale up on a European level. So that was like a natural progression from the NordicWay1 system that we designed. And also it's important for us to have this minimum effort for the data exchange, because it quickly showed that there was a lot of actors involved, and for every new actor you wanted a minimum amount of extra effort from the ecosystem, or from each actor to be able to share to more new actors. We'll get back to more of these goals later. First, I'd like to start maybe with an example of what we're trying to achieve. So for instance, you have us, the Norwegian Public Roads Administration, and we might want to share information from our road network concerning incidents that's been on the roads, like if there's a slippery road, for instance, a vehicle has detected that, or if there's an accident. Now, this type of information can be available from a lot of different sources, from car manufacturers, back-end systems, or maybe like road assistance companies like Falk or Viking, perhaps, or other actors as well. And also these different service providers might also be, or probably will be, interested in information that the Norwegian Public Roads Administration has about the road network. So like road conditions, whether or not there's road maintenance going on. And this is information we obviously want these actors or these people to have. All probably want to share this to as many people as possible. Now the problem now is, or has been, is that this information, even though the information is available, and even though these companies want to share this information, they're kind of locked down into the company databases and systems, and the usual way to do it was to just have like these ad hoc agreements and connections. That's not a very good solution. The same way goes for us, even though we do have some data sharing capacities, like for instance these national access points. It's still not a good way to share this, especially real-time data or near real-time data. It's not really suited for it, wasn't really designed for it. It's more for long-term planned events, for instance, like roadworks. Okay, so that's what we're trying to achieve. Now, the problem that we have is not a lack of data formats. It's important to remember that there's a lot of different data formats available in this sense. That we have a lot of data formats like DataX, and we have the Etsy stack as well with the different denim messages. We can describe a lot of situations in the road network today with standardized formats that are more or less able to be interpreted by anyone. The problem is that we lack a sharing ecosystem, an ecosystem for sharing this kind of information efficiently. Now, I like to break down the problem into two. So the first thing is that there's no way to know which actor has which information. So who can I go to get this information? That's something that you kind of have to talk to a lot of people, basically. Now the national access points solve that problem for the reverse, for the national road operators, but there's no such thing for all the other actors involved in this type of ecosystem, like for instance the OEMs. And like I previously touched upon, the existing solutions mainly rely on this one-to-one bilateral ad hoc data exchange, where it's very expensive to build this, because it's like once you've invested all this time and money into it, you just have one connection to one company, and there's some certain amount of tailoring needed for every new connection that you need. It's also very hard to maintain, and obviously it's virtually impossible to scale this when the amount of actors involved gets very large, and into the like thousands of interested parties. So the solution that we have tried to build now, call it the Interchange network. It's an evolved solution from that we started on back in NordicWay 1, where the scope was maybe a bit smaller. It's an AMQP-based solution. Stands for Advanced Messaging Queuing Protocol. And it adds upon the AMQP service, it adds automated service discovery, so you can be able to figure out what kind of data is available from where, and it also automates the data subscription part of data exchange. The work that we have done has been picked up by C-Roads, so now it's been developed into a more harmonized specification that has been released by C-Roads. You can check that, it's in the hybrid specifications. And the NordicWay 3 interchanges will now be harmonized with that work from C-Roads, even though the solution from NordicWay 2 is pretty similar already. Some small tweaks are required, of course. So it works by having several message brokers. So in this picture, maybe I can have like a pointer here. Where's the pointer here? No. Works. So I just painted one now. So this will be for Norway only. And on the top here, we have a messaging broker that are called interchanges. These message brokers, and they gather data from different service providers. Here I've just taken 3 random examples of service providers, and these interchanges could be privately or publicly run. In Norway, it's operated by Bouvet, but it could be operated by the MPRA as well. And then each of these interchanges keeps track of what data sets each of its attached service providers provide. So it stores metadata on the data sets that the MPRA, for instance, provides, and the coverage areas for these data sets, what types of data it is, the data formats it provides, and obviously who has provided the data as well. And all of that is kept track of inside the interchanges. And then the interchange, or that information about what is available, is then shared between different interchanges. So here you can see that I've attached a Finnish interchange. Obviously, this will be a network of multiple. I've just drawn two of them here for Finland and Norway. But the information that is available from the actors attached to the Norwegian interchange is then shared to the Finnish one. And vice versa, the information that is available on the Finnish interchange is shared to the Norwegian one. So they all have an overview of where to find the data sets and what the data sets are and what they can provide. So, for instance, if one of the actors, like, I don't know, Vaisla, wants to know about traffic accidents in Oslo, it can tell the Finnish interchange that I'm interested in this data set, or I'm interested in this data. It doesn't even need to know whether or not or where that information is available. It just says, I'm interested in accidents in Oslo. Could you provide me with that? And since the Finnish interchange already has exchanged information about what kind of data sets are available, it can then set up a data stream to Vaisla, if they are interested in that, with that information, a data stream that matches these criteria. In this case, traffic accidents in Oslo. And the provider, which could be PALP, for instance, and it could be the MPRA, doesn't need to do anything to facilitate that. So it will automatically, if it says that it wants information about traffic accidents in Oslo, it will be automatically provided as a data stream to, in this case, I guess it's InfoTripla that is interested in it. And if a new provider, for instance, Falk, suddenly starts to provide this information, it will be automatically added to that data stream, like you see here, without InfoTripla needing to do anything. Or even the new actor doesn't need to do anything either. It's just automatically added to the provided data sets by the Norwegian interchange, and then that information is picked up by the Finnish interchange, and the data stream is attached. So it's very low setup and very low maintenance for the involved service providers. You just provide your data set, tell the system what kind of data sets you have, and then you tell the system what information you're interested in. That's it. Everything else is automated. So that's the basic working of the system. We have this more specifically for the Norwegian, and I guess also the Finnish partners run this implementation. We developed it as open source. It's been developed by NordicWay on behalf of the Norwegian Public Roads Administration, and it is available on GitHub for download. You can just go to this link and look into it, download it, have fun with it. It's a pretty large system, so you probably want to run it on a cloud service or something like that. But you can go there and have a look at it. And there's also some information available there, but it's more specifically targeted to this implementation. Okay. Let's see.
So my name is Halvor Grønås. I work as a lead data scientist in NordicWay. I work in data engineering and data science on different technical domains, amongst them ITS, intelligent transport systems. And my co-presenter today is Lars Gyve, who is the key account manager in NordicWay, but I will actually handle the actual talk. And today we will talk about a system for automatic speed adaptation to handle bottlenecks in the road network. That's quite a mouthful. We'll get back to that very shortly. But first, the compulsory plug for our workplace. So about NordicWay, we are a Norwegian consultancy. We have 13 office locations in Norway and Sweden. The number is quite rapidly changing, but we are over 1,500 employees, and we are listed on the Norwegian Stock Exchange. Our core activities is to provide services around design, development, and implementation of IT solutions and digital communications. So, first, some project background. So in the rural areas of Norway, the road infrastructure often has quite limited capacity. And in some places, you have so-called bottlenecks. That is basically stretches of road where two vehicles cannot pass each other. Sometimes that's limited to heavy traffic, but sometimes that's also is down to private cars. These bottlenecks can be road stretches, or they can be, as you see here, a narrow bridge, or an even more hardcore case, an underwater tunnel. So this is the challenge for the Norwegian Public Road Administration, because a lot of the industrial production in Norway happens in these rural areas. You have salmon fish farms, energy production, aluminium extrusion, and so forth. And of course, with industrial production comes quite a lot of traffic, and in particular, a lot of heavy traffic. And you can think, for instance, if you are transporting salmon from a salmon farm, and your trailer gets stuck down in an underwater tunnel, and there's no way you can back out with these semi-trailers. You need to have a crane car to pull them up, and you get congestion on both sides. It's complete chaos. And your cargo is highly time-stamped, then that is a big issue. Now, to build new infrastructure or to extend the infrastructure is very, very expensive. So what the Norwegian Public Road Administration have been thinking about is if there's any digital ways to get around this that is more cost efficient. And more specifically, they launched a kind of proof of concept project where we were involved, where they defined one test site, which is this Skjervøya in the north of Norway, where Aurora Lerøy has a salmon production facility, and where there is a lot of salmon being transported here from the facility across this Skatter Sound bridge, along the coast of Kågen, which is an island, and then across the Maursund tunnel, and then finally to the mainland and to the destination, which can also be in other Nordic countries, such as Sweden, Finland. So let's see what we have actually done in collaboration with Statens vegvesen, Swedish Norwegian, is that we have developed a prototype system that tracks vehicles using the mobile phone as a platform, and so the GPS and gyros and so forth. And that location or that navigation information is then transmitted to a service in the cloud that we developed, that basically predicts future positions of the vehicles. And if it sees that pairs of vehicles are in potential meeting conflict inside one of these bottlenecks, then it sends a speed advice signal back to the mobile application, which then conveys that message to the driver, so that speed can be changed and the meeting avoided. So what you see here on the right side is an animation from one of our initial simulations, where we have cars moving from the top here, from Aurora Lerøy, and coming from the mainland here on the bottom. And if you have pairs of cars that are in potential conflict, then you see a red line between them. And then the car that is being controlled by the system, it gets the same color as the corresponding bottleneck. So for instance, these cars are green. That means they are controlled to avoid meeting in the Maursund tunnel. And if you see a red car, then that is being controlled to avoid meeting in the Skatter Sound. So that's basically what we have been doing. This is 80% of this project, and I'm going to drill a little bit down into detail. First, a little bit about the system at a glance. So we have one mobile app with a front end. So its job is to collect GPS data and transmit that to the cloud backend. It also receives speed advice from the speed adaptation system in the cloud, and communicates that to the driver, both through a graphical user interface, but also through speech synthesis, as seen on the right here. And the speech synthesis is for safety considerations, the preferred means of conveying information. On the cloud backend, we receive the navigation data from the vehicles that are involved in the speed reduction. It then predicts potential meeting situations. It calculates speed advice and pass that speed advice to the mobile apps where it's conveyed to the driver. And then it also has the job of persisting data and holding map data and enrich data from and then navigation data and so forth. Now, developing and deploying such a system is far from a simple task. I'm just going to touch briefly upon a couple of challenges now. So up to the left here, we have the aggregated traffic flow on one of these at a point in this test area, inferred from one of Statens Vegvesen's induction coils embedded in the roads. So these are actually magnetic flux measurements which can use to decide on the speed of the vehicle and the direction it's traveling in. Also you get like a profile that can be used to kind of infer what kind of vehicle it is, and you at the very least get the length of the vehicle. So we had data from these for about half a year, and we used those to get the picture of the traffic flow. And so in red here you have basically scooters and motorcycles. Green are car with hangers. There's a lot of those in Norway. The blue ones are kind of private cars. And the orange ones are the ones that we are the most concerned about, which is kind of heavy traffic. So here you see the traffic flow as a function of the time of the day, basically. What you see here is, yeah, of course, it's a lot of traffic in the middle of the day, and some quite a lot in the morning, even early morning. More importantly, you see that the orange traffic, which is the one that we are actually initially controlling potentially, is quite a small part of the total traffic flow. So that means a lot of the actual traffic is not controlled. That obviously makes it more difficult to predict future position. Then also, many of these areas are also quite hardy in regards to the weather. I pulled this picture from the homepage of Skjervøy Hockey Club. This is actually quite a nice day. It can be very windy and rough there, and of course that also affects the driving patterns that can vary quite a lot in regards to also to what is safe driving speed. And then we see here, these are raw measurements from the induction coil. So this is actually forms the basis of the plot that you see above here. This is a time series plot. And you see there's a lot of variation in the speed people are comfortable with in an area where you actually have a nominal speed of 60 kilometers an hour. And in the end, you know, humans being humans, there's a psychological factor here. If you have such a system, you get advice. But you know, you're not always following them. Although either because, as mentioned earlier, you cannot follow them, you're stuck sandwiched between smaller cars, or just because you know you're distracted, or you don't really want to follow the advice. Basically, if you feel that you get nagged too much. So that's some aspects, and then there's kind of some basic physics of the problem. So. If you consider the following case, if you have two cars approaching each other from opposite directions at a nominal speed of 60 kilometers an hour, this plot shows that the kind of the shift that can achieve between them as a function of change in relative speed on the x-axis here, and then the start separation between them on the y-axis. And everything this gray here, it means less than 1 kilometer change. So what you see from this is that actually you need to control speed over quite long distances, and or you need to have relatively significant speed adjustments in order to effectuate significant changes in the meeting point. So that's basically a fundamental constraint on the concept. And looking at this, of course, another kind of concept that immediately comes to mind, and maybe came to mind, even before we started this speed adaptation thing, is that basically having some kind of digital light signal, which gives stop and start, is an alternative solution. You get a very radical speed change from down to 0, basically, and you can resolve some situation quite fast. But of course, that is also not always possible in all these areas. There's no space, for instance, to stop at the roadside and so forth. So that's just a side comment on that. Let's move along. We'll talk a little bit more about this kind of the core functionality, the speed adaptation engine of the system. There's of course a lot of plumbing and API stuff and so forth going on. Also, first of all, a key component for the development of this project is the simulation framework that was developed. Was very key. It's not like we could just wildly start testing with real cars up there. I think no one would have wanted to be part of that, at least initially. So what we did is that based on this data from these magnetic induction coils that Statens vegvesen have deployed in the area, we generated a simulation framework that makes synthetic data. Basically, it tries to, or it provides cars, with going with the same kind of traffic flow as we have observed in the area, or we can even crank up or down the traffic flow even more if we need to test different scenarios. And that was very useful for algorithmic development and enable us to do rapid prototyping and testing of new ideas. And we also used hardware acceleration to speed up the computations and to improve the visualization. And visualizing it is actually quite powerful way to get in the hang of how things are going. I was actually planning to have a live demo now, but based on the kind of feedback I got about videos and so forth, I think I will skip that and instead just show you a brief kind of video from the actual simulator that we used. It's fairly similar to what you have already seen. Let me see. So we can just start it here. And this is actually 3D simulation. So if you wanted, if I did it this live, I could actually zoom down and you can look at the details down in the down at the road level. So the road model that is used here, both in simulation and in the actual system, is from the Norwegian road database that is owned by Statens vegvesen. And again, kind of what we saw earlier, here you see pairs of cars that have like a red line between them, and you see that at least one of the cars that have a red line between them is changed its speed as it approaches the bottlenecks that are delineated in green here, so that there are no meetings between these two green points. And that is basically job done. Once again, going from the simulator to the real world, you have a lot of practical and technical challenges. Operation on actual road data, handling of GPS signals. We have real cars driven by humans at some point. So I just want to, there's a lot to say about that. I just want to very briefly mention one example. So we have a GPS location from your mobile phone. That is a noisy measurement. So what you first need to do is to convert it to the same coordinate system as is used in the Norwegian road database. Then you need to project that noisy location onto the road. So you need an algorithm for that. That is so-called snapping. And then we project it from the road onto a linear reference. So basically, if you collapse the 2D representation to coordinate representation of the road onto a linear line, that is actually what the system is using when it's doing calculations. And then you need to convert the bearing information into a direction if it's going up and down. So that's simple when speeds are reasonably high, but if things slow down, for instance, we have congestion, then it can, because of noise, get confused. So that also needs to be handled. So the last part, I'm going to talk about the test that we did in Skjervøy from the 6th to 7th of March 2019. We had 4 cars with the drivers from Statens vegvesen driving back and forth in this test area that we now talked about. Here you see the beautiful surroundings and also 3 of the cars that were being used. So once again, here is test area. We've gone through that before. I'm not going to say too much about it. Just mentioning one more fact. In addition to the bottlenecks, there is also the Kågen tunnel. That's almost back to back with the Maresund tunnel. And even though Kågen tunnel is not a bottleneck, it has 2 cars can pass. You then have actually a resulting system of almost 4 kilometers without the GPS signal. So that was kind of one technical challenge also that we had in this area. So here is basically a time series plot showing some test results. We have the linear reference here on the left side, and we have the timestamp here on the y-axis. And here we have the position of the cars. So basically, the 2 black lines here is the limits of the Maresund. No, this is actually the Skattersund bridge. And so basically what you don't want to see is that these lines cross each other inside these 2 black lines. So that's what the system is trying to achieve. So here first we start with 2 cars driving towards each other. And you see at one point here, the slope of the speed changes, and that is basically when these cars started to receive speed advice and lower the speed. And you see they meet just outside the bottleneck. And then the pattern continues the other way, and then you have 3 against 1 car, and yeah, the other direction, and 2 against 2. Here we have a waiting situation. There was actually a fire in Skjervøy this day, and so there was a lot of emergency traffic and also some press traffic and NRK and so forth. So a little bit unlucky about that. And at one point, one of the drivers felt like, okay, I actually need to just continue driving, and since this bridge can accommodate small cars passing each other, he just went in there, and so you see here, this is the only actual meeting situation. So the system worked quite well. We completed 16 tests, and we, depending on how we count, 31 potential meeting situations, and 29 of those were resolved through speed adaptation. Challenges: very latency in the system. Sometimes the target speeds were kind of impractically low, and also noisy speed advice coming in maybe a bit too often. We have good technical solutions for that, but that's some of the things that we observed during the test. But all in all, very, very happy with the results. Before I finish, I've talked a lot now. Here are pictures of several of the doers. Give a big shout out to them. Particularly to the left here, our project sponsors and supervisors from Statens vegvesen, Torgeir Vaa and Christian Berg-Skjetne. And then there's Lars here and me, basically talking, and here the core technical team. Thanks for your attention.
We will now go further on in the presentations, and we will now have presentations related to pilot sites at E8 in the Skibotn Valley. We will have 3 presentations from the companies ITS Perception, Q3 and Triona. And we will sum up the questions after all of these 3 presentations. So we start with the ITS Perception, and I say welcome to you. So please start the presentation.
Okay. Is this on screen now?
Yes, it's okay.
Okay. Hello. So ITS Perception is a small technology supplier and focusing on sensor-based technology and related services for transport infrastructure and mobility applications. So my name is Hans Petter Flugstad. I'm the CEO of the company. So I will go through our experience as a participant in the E8 Borealis pilot project and what we've done there, and we'll present the technology used and the perception system, and also how we communicate the data.
Hans Petter, we don't see the whole presentation, so could you try to start it once more?
Okay. Is this on screen now, or?
It could work like that, so it's no problem. So go on with this presentation.
Okay. Okay. So we participated in the E8 Borealis pilot project. As has been mentioned, this was project addressing challenging weather conditions and road conditions, and a lot of problems related to mainly heavy trucks. And it was also a project where the NPRA wanted to test different technologies to solve and overcome some of these problems. So from a supplier's standpoint, this was an interesting project, as we were only presented with a problem statement, not given a set of requirements. And so it was an interesting way of working, but it was also a challenging way of working. So we actually started off just by pitching an idea to and then developed a concept then that was later developed as a sensor system based on LiDAR technology and image analysis for perceiving data. So the sensor we developed can provide sort of automatic incident detection and distribute the events to the NPRA systems and also other external systems if needed. So the main principle in the sensing technology is using light. So the sensor emits a light pulse, and if it's any objects in the field of view, reflections from those objects will return back to the sensor, and the sensor detects the reflection and by measuring the time it takes from emitting the light pulse to the return is received back is used then to calculate the distance to the object and also the size of the object. As the light is distributed into several segments, we can detect several objects in different distance from the sensor. And the sensor uses a digital signal processing so that the signal is enhanced somewhat to eliminate noise and reflection from minor objects like snowflakes or things like that. So, and it's also a solid state solution, so it means no moving parts. And we thought that was significantly given that it was supposed to operate 24/7 in an Arctic harsh climate, and it has proven to work very well. So the perception system we have built is then based on the LiDAR data, which gives us dynamic object detection. We get a precise distance to the objects in the field of view, and we can also calculate then the position of the objects, and we of course can extract the speed and direction of objects moving on the road. And when we detect any normal, not normal traffic, for instance, if a car slows down, we will then use image analysis to classify and do object recognition. So it's a two-step solution. And then finally, we can share this information if any defined event occur, like a truck has got stuck in the hill. We can then share this event to the NPRA as a then message. We have implemented different types of messages to distribute. And we can also, in the case of E8, we have integrated with the NordicWay node, but we can also share data locally through to a radio, like radio or G5 network. Okay, so that was my presentation. Thank you.
Okay, I am Ola Martin Lykja from Q-Free. I'm working in ITS department of Q-Free in Oslo. So we entered into this project through innovation competition in 2018. So the system is designed to, it's about using lots of sensors in the ground to detect the stopped vehicles and slow moving vehicles in this hill. In the Borealis at the A8 in Tromsø between Norway and Finland. Yeah, lots of you have already shown pictures from the winter, so just to illustrate this stretch of road that we are installed the sensors in. Each red dot represents one sensor in the ground. every 5 meters. This system, it's a magnetic sensor that is retrofitted from a parking sensor, which is the main product. The parking sensor is embedded into the ground, into the road surface, and it detects vehicles on top of it. The main sensor is a magnetometer sensor. That means that it's independent of snow, ice, and weather, and light and day and night. So it doesn't degrade when the weather is the worst and you need the sensors the most. There is also an optional radar in the sensor. This was not used in the Borealis project. There is a battery. So there is no power cables. You just put it in and it stays there. It communicates with the base station using the IMS band. There is security built in, so it's not possible to manipulate the sensor readings without the correct encryption keys. And it's also privacy, because there is no identifying information in the system. There is no photos taking or license plates or anything like that. Just seeing the presence of vehicles. So we installed 120 sensors, 5 meters apart, in the middle of the right uphill lane. Because of the technology and in the sensor, it was sensing pretty slowly every 2 seconds. So that means that a car that is driving fast is not seen by every sensor. But the large number of sensors creates some kind of spatial redundancy. So while driving uphill, vehicles are in general seen at some sensors. The main focus of the application was to detect slow-moving vehicles and stopped vehicles, and in this case, it's no problem with the kind of slow response of the sensor system. Installation was done in the fall of 2 years ago by drilling into the road and putting the sensor down and sealing it with a cement-based sealant. We had tried to do this in the parking lot before many times to install, and it was pretty quick, but in the road, in the cold weather, it turned out to be some more work than we anticipated to do the actual installation. Yeah, so the final, after sensors when it's installed, it's almost invisible. You just see a small gray circle with a sealant showing. So it's invisible, and it's also mounted below the surface, and the sealant is in flush with the surface to avoid snow plowing trucks and to tear up the sensors. Yeah, so there is some wear and tear also from snow chains. So the first winter there was 2 sensors that was the cover was destroyed. So in all the installation in the road worked pretty well. There was 2 base stations installed, one at the top of the hill in question and one at the bottom. And Erlend from Aventi took this very nice picture with the Borealis in the background. Yeah, so we have a sensor network with 120 sensors communicating over a radio to the 2 base stations in towers. The towers were connected to the fiber optic network that Jorunn talked about. Data went onto a cloud server where it was analyzed, and the result, the vehicle detections, was fed to the traffic management center, And we also developed visualization tools to examine the performance of the system and help us develop the system. So what does the raw sensor data look like? We get a lot of readings from each sensor when there is an obstruction above the sensor. So we get kind of this very noisy picture. But when we have a large truck that they are 20 meters long, it will typically cover many sensors at a time. And then when it's driving slowly, it will stay above each sensor sufficient long to be detected reliably by each sensor. But a small passenger car moving at full speed, 80 km per hour, will not kind of create this cluster of dots. It will just be random noise points in this picture. But again, the focus is on the slow, to detect the slow moving traffic. It is so it's not you cannot use the system as a speed trap. The scale on the y-axis is the sensor installation point, so it's the 600 meters hill we see on the y. The software will try to find these clusters belonging together, and then it will draw a line in the visualization tool to connect the dots visually, literally. So we can, and then you can look at each vehicle as a line going sloping up the hill. So for example, the one highlighted here is a vehicle traveling at 57 kilometers per hour on average. If the vehicle was slowing down, we will see that this line would curve to the right, and it will also have more denser dots on when the speed was going down. Sometimes we noticed that there was some lines were sloping the wrong direction. So this line here is sloping to the left. We figured this out finally, and it is someone driving downhill in the night in the wrong lane. So it takes a shortcut on the left lane going down. So this turned out to be very, very common at night to people taking the shortcut. So one output from the system is that you can see how this average speed of the vehicles are. So in this diagram you can see the number of vehicles every day in each speed group. So on the top we have up to 90 kilometers per hour. And on the bottom we can see that there are some vehicles moving very, very slowly below 40 kilometers per hour. So this is one data point for each day over 3 months. And the y-axis here is the number of vehicles. The numbers here, you can see there's up to 500 vehicles a day. This corresponds pretty closely to the average number of vehicles per day on this road. So the algorithmic challenge here was to connect the dots, to move from the snowy, noisy dot image to vehicles, and to find out what dots belong together. We tried a few different methods, but we found out that this particle swarm, particle filter type method worked the best. So each dot, raw dot measurement dot, was assigned a number of, we created a large number of probable vehicles with different speed profiles for each measurement. And then the system was driving forward in time and estimating the future position of these particles, and you ended up with, and then you could calculate the score based on how many dots that was touched by this speed profile, this particle. And then only the particles with the highest score was kept and classified as vehicles. So this is the basis for these line drawings we just looked at. We tried some other methods that was discarded, but we did not try a machine learning approach. We tried to promote this as a master thesis for machine learning at Trondheim University, but no one took it. So this was not explored. We had some discussions with the professors at NTNU about this, and they questioned the quality of the training data, and they also question if this was very applicable to a machine learning. So this was a little bit surprising to us that this was not, no one wanted to explore this. So the field is still open. Please raise your hand and take the challenge. We have tons of data to work from. The sensors also collected some auxiliary data, ground temperature. So this plot here shows the temperature during 4 weeks of May. So you can see that there is quite a large difference between day and night temperatures. So we also examined the difference in temperature between the upper and lower part of the hill, and you could see from sensor data that there are actually a temperature gradient in this hill. Very small, but it's visible in the data. Yeah, the validation of the system was a question for us, but we used the magnetic loop detectors. There's a magnetic loop detector at the top of the hill, so we knew when vehicles were passing out of the test field, kind of. So we used this to compare our sensor data and our vehicle estimations and classifications and speed estimate to the loop detector data. Correlation was pretty good for large slow-moving vehicles, but as we knew from the start, the small passenger vehicles was not always detected. So this diagram here shows detections during 24 hours in the winter this year. So the top line is the number of vehicles for each hour during the day from the loop counter, and the other lines on the bottom with different average speed, different speeds are what we detected. So you can see that at night, where you mainly have big trucks, you can see that we detected 80 to 100% of the vehicles. But during the day, where you have more passenger cars, the discrepancy between the loop counter and our data is larger. We also looked at this specifically for slow-moving vehicles, and didn't show that here, but there is also the question about the placement of the loop detector. This is a little bit on the top of the hill, so that some heavy trucks may have different speed at the loop detector than in the steep hill. We also use camera systems for validation, or try to use it. This is not the same camera as ITS Perception is using. This is a slower camera that was on the top of the mast on top of the hill. We had some problems with the streaming of this from this camera, because sometimes frames was lost, so we could not use this reliably to validate the system performance. So in the picture you also see the installed sensors and also the reindeers. This has been shown before. Yeah, we have also, so in Borealis the radar was not used, but we have done some research in Q-Free in parallel with Borealis to enable to use the radar. So here you can see an example of a radar sensor strapped to a tree looking at cars sideways. I'll just go through the last slides pretty quickly. So this is another sensor application we have looked at, avalanche detections. It could be possible to apply the same type of sensors for this purpose. The problem that Beauvais described with narrow roads without any meeting possibilities, you could use sensors to augment the data they get if there is no mobile coverage in that area. Short mention of that. Yeah. So the work we had planned for 2020 did not work out the way we had planned because of travel, the restrictions for the COVID-19. This was a little bit unfortunate. And we also had a long period in the end of the winter with the network problems. Our summary and conclusion is that it is possible to use magnetic ground-mounted sensors for this purpose. Battery life is a challenge, so you need to do a trade-off between what kind of latency you want in your data and the battery life. Migration from this proprietary ISM band to narrowband IoT or Cat-M1 mobile technology will probably reduce infrastructure needs and reduce maintenance and installation cost. So we think that this kind of technology is suitable for low volume roads in remote areas. Thank you very much.
Do you see it?
Yes, it's okay.
Fine. My name is Rune Draksnes. I work for a company named Triona as an CEO. Triona is a Nordic IT company with offices in Norway, Sweden and Finland. And my working place is at Trondheim in Norway. Through the Borealis project, Triona, together with Euroshield, has developed an ITS platform for controlling road signs and integration with the various types of sensors. The goal for the project was to make a smart sign, a road sign, that are controlled using a ITS platform and a web application. Make a platform for collecting and visualize sensor data, and make a autonomous decision for displaying information on road signs. And the last goal was to offer a platform that can be integrated with other external systems. Borealis is defined as a pilot project for testing new technology, but we quickly saw the need to be able to test the equipment before it was installed on the road sites. The reason for this was lack of infrastructure at the test site and the need to greater control in the initial phase of the project. Together with Euroshield, we established 2 test labs, one at Euroshield in Tønsberg and one at Triona in Trondheim. And we established a VPN connection between the labs, so it was possible to do remote testing between them. The picture in the presentation showed the test lab at Euroshield in Tønsberg. Here you see the various installations that we did during the project. At location 1 in Lullemoen, an RGB sign was installed combined with a weather station. At location 2 in Hellingskogen, an RGB road sign was installed. At location 3, there was no road sign installed, only some sensors, and we didn't install a weather station, a visibility sensor and a surface sensor. At location 4 in Gardermobakken, a single RGB sign was installed. This image shows the system and how it is configured at a high level. The basis for the solution is an ITS controller located in all the locations. The ITS controller is responsible for collecting data and performing action defined by the ITS platform. The ITS platform operates as a SaaS solution, software as a service, but continuously receive data from all the installation. From the ITS platform, you can read data using a separate web application, carry out autonomous control of road signs. You can control signs using an API. And you can distribute sensor data using message queue or API. A total of 10 ITS controllers of different brands have been installed on the 4 installation. The system is redundant. If 9 of the ITS controllers are damaged, the 1 remaining can still handle all the 4 installations. The purpose of this is to be able to evaluate different hardware solutions to get experience for the future installations. And in case of error, you can, in many cases, fix it remotely by doing a remote configuration of the system. An important component of the project is a web application that interacts with the ITS platform. Here you can see the installation in maps or list views. You can also get indication of the status of any installation by looking at symbols and the color of these. Red color indicates that something is wrong and need to be fixed. Yellow indicates a warning, while a green color indicates that everything is okay. In the picture, you see two symbols that are focused. The one symbol has a green color and indicates that everything is okay. But the other symbol is a blue circle with a number 2 inside. This indicates that you have to zoom in to see the state of this those installations. You can also define your own images and symbols and upload them to the platform. And from a list of preloaded images, you can choose one to be displayed on the road sign. Some of the signs selection also contain simple autonomous function that responds to sensor data. Currently, you only have the option to display real-time data, such as wind speed and temperature. But we have an option of different warnings based on sensor data and events from other external systems. You can also view real-time data and historical data for a defined time interval. Which kind of data who can be displayed will vary depending on which sensor are installed in the different installation. For the Borealis project, there are 3 sensor types connected: the weather station, the visibility sensor, and the surface sensor. And by using this sensor, you can read data type like air and road temperature, humidity, pressure, wind direction, wind speed, visibility, and so on. You can also see how the equipment is configured on the different installation and make change due to new installation of equipment. For all type of sensor data, you can define what is a valid value range. If the measured value is outside of this range, an error message will be flagged in the system and indicated in the maps and so on. If you get an error situation, you can retrieve details logs. For example, if an RGB road sign has stopped, or the network is down, or the sensor data exceed the defined limit. Based on the Borealis project, Triona and Eurosylt have further developed the solution into new products. We have a product called Warning of Wild Animal. This is a product for alerting drivers to the danger of wild animals on the road. We have a product named Warning of Height Restrictions. This is a product installed at road with height restrictions like tunnels, and the driver will be automatically notified by the road signs if the vehicle violates these restrictions. We also have developed a product named OPC UI server, who is a product that allows the road traffic center to communicate with the solution in collaboration with the road signs. And at last, we have developed a control station, who is based on the same ITS platform used in the Borealis project. This is something used to simplify the work related to control of vehicle. We have a simple solution with manual control and a more advanced one that uses automatic number plate recognition, live measurement of weight and so on based on sensor. And this advanced control station also have integration with the external system like AutoSys. Then this was the end of my presentation. If you'd like to have some more information, you can send me a mail on this mail address shown in the presentation. Thank you.